Very well. Welcome back. Hope you enjoyed your break. We're back here at Swiss Cyberstorm with the second to last talk. We welcome Dr. Ksenia Peguero, who did her PhD on the topic, on the research she's presenting to us, and this is about the security of JavaScript frameworks. Please welcome Ksenia Peguero.
Thank you very much. Thank you. All right. So, very happy to see you here. Very happy to be in an in-person conference. First time for me since forever. I am a senior manager of research engineering at Synopsys Software Integrity Group. And what we do is we have a lot of software products, security products, SaaS, DAST, you name it. And my group does research that then goes into the things that security software finds. So rules, checkers, whatever you call it. So what we do day to day is we'll look at a lot of code, a lot of frameworks, libraries, languages, technologies, and trying to find things where developers make mistakes. So this is what I do day in and day out. On the side, while doing that, I was also getting my PhD, which is finally done. I'm very happy to be done with it. And I also have 2 children. They also take a lot of my time. So now I'm going to just give you a very short version of my many years of research that I was doing. OK, so we're going to start with some background on JavaScript frameworks. And then I'm going to talk about 3 use cases that we looked at for client-side JavaScript, server-side JavaScript, and desktop JavaScript, and the frameworks that are used in these different aspects of JavaScript and how they affect the security of the applications that are written using those frameworks. So why JavaScript? Well, JavaScript has been #1 most popular language for many years. According to Octoverse reports, since 2014, it's been language #1 on GitHub. And if you write code in JavaScript, then, of course, you're going to use frameworks. So I love this quote. And this quote is from 2012. So it's a little bit dated, 7 years later, right? But it's still the case. There are so many JavaScript frameworks. So how do you choose one? That is the question. And there are frameworks for client-side, Angular, React, Vue, many others. There are ones from server-side. There are full-stack frameworks like Meteor that do full code from client-side to server-side. All the communication, everything is in one language, in one ID, and one developer can do it all. And of course, there are desktop frameworks like Electron, and there are JavaScript frameworks for mobile applications. So whatever type of application you pick, there will be a JavaScript framework for it. So when we choose a framework, when developers choose a framework, do we as developers think about security of the framework? Not really. The first questions that we ask is, does the framework have the functionality that we need? Does it do what we need? Does it have the performance? Does it have good documentation, good support? Is it backed by Google and Facebook or somebody else, right? Or is it very small niche framework, and maybe if you find a security issue, nobody's going to fix it? But that security question is not often asked at the beginning. So following the shift left paradigm, when we say we want to fix the code as early as possible in the software development lifecycle. And I was thinking that, OK, well, what if we can prevent the mistakes instead of fixing them, right? Can we go even farther left on this spectrum? So I came up with this, I came up with a hypothesis that if the fix is closer to the framework, it's going to be easier for developers to not make security mistakes. And my colleague, ex-colleague John Steven, came up with this levels of mitigations. So if software has a vulnerability, it can be mitigated in different levels. And it can be mitigated by a custom function. So a developer writes a function that, for example, does sanitization, right? or a developer uses an external library, some third-party code. Then this is level 2. Level 3 is it's a still external library, but it's a plugin for a framework that developer is using. So it works more seamlessly with the framework. And then the 4th level of mitigation control is when the mitigation is built into the framework itself. And as I started this research on the academia side, there should be also the baseline. So I have level 1 where there's no vulnerability, there's no mitigation itself in place, so there is vulnerable code. Let's look at some examples. So level 1, it's a function that, as I said, developer writes. So the well-known XKCD comic where you have get random number generator, right? Writing your own crypto, we all know don't do that. So if a code is written by developer, it's likely it will probably not be super secure. So, OK, XKCD comic is all funny, but this is a real example of the course function for JavaScript that sets headers. And if you ever worked with cores, you can see that it's setting the access control allow origin to star, which means we allow any origin to get request data from us and to be able to read the response. That's probably not very secure unless it's a publicly accessible website with public data. So then level 2 is an external library. So a long time ago, there was an ISAPI library that's developed by OWASP. So it's a library that was doing all kinds of sanitization, and you can pull it into your application regardless of which framework you use for the applications, like third-party library. Level 3 would be a plugin that works seamlessly with the framework. So for example, CSRF is a plugin for Express framework that allows to generate XSRF tokens. And the third one is a built-in security. So a good example would be Spring Security, which is kind of sub-framework of the Spring framework that has a bunch of different security tools built into it. Authentication, session management, a lot of controls that are already built in. So to look at if this hypothesis stands, if the mitigation is closer to the framework, it makes a secure application. We need to do some experiments in academia. In the industry, it makes sense, should be true, right? But in academia, it's like, well, give me the data. Does it actually work this way? So in my first case study, I took client-side frameworks. In this case, I took actually template engines. That was in 2016, a long time ago. So client-side JavaScript. And so 3 frameworks/template engines, Jade or Pug, EGS, and AngularJS. Nobody probably remembers them anymore, because that's how fast JavaScript progresses. And I took 170 applications that had a specific use case, right? So finding open source applications that have a cross-site scripting, that was the goal of the study, right? I need to find applications that tend to have cross-site scripting. So I needed to have a special use case. And the special use case is that the application should render user input and require some kind of rich context. So that's why I chose to select specific types of applications like blogs and CMS systems, where we want to give this opportunity to the users to be able to inject images, bold text, whatever, some rich content, as well as cross-site scripting, of course. And so what I did is I got a bunch of applications from GitHub and developed the pipeline to parse and analyze them and find those locations where XSS may be, using different types of parsers for those different frameworks that I analyzed. And then I did the manual analysis of the data and compared also if there are any other factors that could affect the data or not, to make sure that the framework was the cause of the results that I got. So so the 3 frameworks that I chose had different levels of mitigation. So that was kind of the main part, right, to see. So for example, Jade and EGS don't have any built-in mechanism to protect from cross-site scripting, well, to allow developers to display code that is provided by the user in a safe manner. So there is no built-in functionality. So they can either developer has to write their own escaping, don't do that, or they have to use a third-party library like DOM.XSS or something else. Not many applications, turns out, not many applications did that. And then the third framework, AngularJS, had the context-aware escaping that built into the framework. So it had the mitigation at level 4. So looking at the results, we can see that EGS and Jade had a lot of applications that were vulnerable, in fact. So for example, we had 25 and 23 applications out of the 50 or 60 applications. And then applications written with AngularJS had a very low number of vulnerabilities. So it looks like hypothesis stands. Data kind of proves our idea. So then I did the second study. And I took cross-site request forgery and server-side JavaScript frameworks. Kind of same idea. So I needed to have applications that would be likely to have a cross-site request forgery. And cross-site request forgery happens when there is a change of state in the application on the server. So then an attacker can trick the user to send a command that comes from the user's browser. User doesn't know about it, but the browser attaches the cookies. And so the vulnerable application thinks that the request is legitimate and grants the request, executes that functionality, updates some data, etc. So there are different protections from CSRF. The most common one is the CSRF tokens. And there are some proposals on the client side. There are same-site cookies that, again, today are supported by all of the major browsers, their latest versions. But that was a few years ago, so that wasn't as widely supported at that time. And then I will also separately talk about the JWT tokens and how they sort of provide this protection. So I selected, again, a bunch of free open source applications that had this functionality of changing state on the server. So there were blogs, CMS systems, e-commerce websites. And I chose 5 frameworks originally. So Express, Koa, Happy, Sales, and Meteor. And I'll talk about Meteor separately. And my goal was to select about 100 applications for each. Turns out that Happy wasn't as popular, so there were fewer applications that I was able to find that would have that functionality to get that data set. And if we look at the mitigation levels, so Express, Koa, and Happy all don't have this functionality, the protection from cross-site request forgery. They don't have it built in. But they all have a plugin or a couple plugins that work pretty seamlessly with the framework. And then Sales is a configuration-based framework. And it actually had CSRF protection that was built into the framework. So that one had protection at level 4. And I mentioned that also I looked at Meteor. So Meteor is a full-stack framework. And when the communication between the client side and the server side happens, it actually doesn't happen at the HTTP level only. It starts at the HTTP level, and then it uses a different protocol. It uses WebSockets to communicate. So because it has its own DDP protocol that kind of doesn't have all the data sent back and forth with HTTP. So what does it mean for the cross-site request forgery? Well, it means that there is no cookie that's traveling between client and server. And if there is no cookie, that means there is no cross-site request forgery. Because the whole premise of the attack is that the request is sent from the client's machine, from the client's browser, and the browser thinks that the request is legitimate. It attaches the cookie. It goes to the server. Server identifies that the cookie is active from the active session, so it grants the request. If the communication is happening at the WebSocket level, so there's only at the time when the WebSocket connection is established, the cookie may be used or the just authorization is used, whatever mechanism. And then once it's dropped to the TLS level of the WebSockets, there is no cookie. But that also means that the attacker code, if a victim opens an attacker website in the same browser in a different tab, it cannot hijack that, well, it cannot easily hijack that WebSocket connection and send a request, right? There's a way to start a WebSocket connection illegitimately, but that's kind of a different type of attack. But basically, if the communication happens on the WebSocket level, there's no CSRF. So from that standpoint, the Meteor framework, just by the way how it is created and designed, protects the application from the CSRF. And another example is the usage of JWT tokens. Again, if an application uses a JWT token, that means it doesn't use a cookie. The token is sent in the HTTP header, so CSRF attack is not possible. Again, there are other downsides with the JWT tokens, which I'm not going to go into details. But if the application uses JWTs for some reason, the decision wasn't to protect from CSRF, but they kind of come with this benefit that the application is now secure from CSRF. So if we look back at our list of, OK, what are the different levels where the mitigation is happening, now we have this new level where the mitigation is baked into the design of the framework. We don't even need to enable something in the framework or disable something, like with Meteor. It's just built into the architecture. So that gives us level 5, where the mitigation is at the framework itself. So I ran the same pipeline, analyzed the data, and when I looked at the data, the results were a little bit surprising. So it turns out that actually out of the 4 frameworks that I looked at, the one that got the highest number of secure applications, the better protection, was Happy.js, which had the same level of mitigation as Express and Koa. It had a plugin. But realistically, the protection was not because everybody used that plugin, but because developers chose to use JWT. So if you can look here, that the 0 applications had the CSRF protection enabled, 0 developers used the plugin. However, 17 applications use the JWT tokens just because that's how the application was designed, and so they had the highest level of protection from CSRF. And then if we compare the others, for example, Express and Sales have 2 different types of mitigations. Express has level 3, Sales has level 4, but they had the same number of vulnerabilities. So this goes in conflict with the data that I got with my first experiment. And the question is, OK, both 2 frameworks, so AngularJS, for example, and Sales had the mitigation at level 4, but Angular applications were all secure from, more secure from cross-site scripting, where the Sales applications were not. Why? Something doesn't align. And when I asked this question, started looking deeper, well, the thing is that Angular applications, the protection is built into the framework and enabled by default. Where in Sales, by default, the CSRF flag was set to false. And so not many developers went and changed it into true, which leads us to a conclusion that secure defaults are important. And in fact, they're very, very, very important at the framework level. So then I went and looked at the desktop applications. In JavaScript, there is only one really popular framework for desktop applications, that's Electron. So I couldn't compare different frameworks. There was only one. But what I did is I got a collection of 141 open source applications and ran an open source tool, Electron negativity, on them, and then analyzed the data, how many false positives I had, how many true positives, got all the true positives, and analyzed what types of security issues these applications had and how they could be protected. At which level could there be protection if there was a protection? And then the goal was to come up with the recommendations for the Electron framework. So let's see. Yeah, so there were a lot of false positives. Out of 1,200 potential vulnerabilities, there were actually almost 1,000 of false positives. And the reason for that is because electronegativity does not have full data flow analysis. It's like very simplistic AST analysis. And one of the examples which kind of demonstrates the problem is that in this piece of code here, where we create a browser window and we set the parameters and we set the sandbox, and to any human being, we can see that the sandbox is set to true, but the tool, because the variable is set ahead of time, doesn't propagate the value and doesn't know that sandbox is actually set to true in this case, and will report a false positive. So I had to manually triage all of that, and then selected the 8 top vulnerabilities that came up in the applications. And as I said, the question was, OK, how many of them can be fixed in the framework, if they can? So I'm going to give a quick couple examples. I'm not going to go into every type of security issue with the Electron applications and security kind of protection. But there are 3 important parts. So one, there is a setting that is called node integration. What it does is, in an Electron application, a web page is run in a web view, and the power of Electron application comes from the ability of that JavaScript code that's run in the web view to be able and execute functions on the file system, so functions that are a part of the Node.js. And by default, that integration with the Node.js, with the server side, is turned on, which is great. That's kind of where the power comes from. But because it is set by default, if we have some malicious code or just code from the internet or code that's loaded over HTTP and not HTTPS, like whatever can be manipulated, that means that web page now has full access to the operating system of the client computer, right, of the user's computer. And so the suggestion here is very kind of straightforward. We'll turn it off by default. And actually, in version 5 of Electron, it was turned off by default. Similar with context isolation, that's another level of separation between the code that runs in the web view and the server side. What it does, this option, what allows, is to have 2 different contexts in which JavaScript is rendered for the web view and for the server side. If it is not enabled, then what applications can do, what the malicious code can do, it can override built-in JavaScript methods and then call them maliciously on the server side. And basically, because of a vulnerability called prototype pollution in JavaScript, you can override a function such as index off, for example, or creation of an array, and then call malicious code on the server side. So again, usually there is no need to have that same context. And if we enable it, if we enable the isolation of the context, it doesn't have any serious limitations of the functionality, so it should be disabled by default. And again, this was proposed in version 5 of Electron, and then it was never fixed. And I checked recently, and actually, finally, in version 12, this default setting was changed. So with the limitation of time, I'm not going to go through everything. So when I looked at those top 8 vulnerabilities, there are actually 6 of them or even 8 of them can be fixed, that can be mitigated at level 4. And in my work, I proposed the mitigations for each of them of how they can be mitigated in the framework itself. So we could improve the framework itself. And 2 of them actually were improved over the course of time. But there is a rest, right, that hasn't been improved. So the question is, OK, what do we do as developers? It takes a very long time to fix a framework, and it may not be fixed if it also doesn't have enough users and it's not maintained really well. Like, what do we do? So specifically for Electron, what I did is I created a Visual Studio plugin that is based on ElectroLint that developers can actually run in their IDE and find those vulnerabilities kind of as early in the code as possible. So it's not going to fix them, but it at least is going to show the, highlight when you're trying to use a insecure function, or when you are in the security context and you may be making a security decision here. It's going to highlight it and right-click on it, and it shows you the list of possible vulnerabilities, and it also shows you how you can fix the issue, and basically asking a question. For example, you're trying to use here a URL that comes from the user. Do you really want to allow HTTP URLs here, or should you have another check that says only HTTPS traffic if the link comes from the user or something like that? So that is open source, available to everybody. So if you are writing code in Electron, then you should check it out. And I think I'm running out of time. So if there are any questions, or yeah.
Almost caught me by surprise here.
Thank you.
Thank you for an interesting wrap-up of many, many years of research.
Yes. Very happy to be done.
Do we have questions from the audience, please? You're as stunned as I am. I have seen a previous edition of the talk before, so I'm already recovered. You said these JavaScript frameworks are being replaced by new JavaScript frameworks in short succession. I think, yeah, that's the case. Is that slowing down, question one? So are there new kings of the hill establishing themselves and they're here to stay? And do you see the new contenders having better security capabilities than the older ones that they're replacing?
Yes. I mean, luckily, for example, if as I said, the client side, those frameworks were very, very old. And for example, AngularJS was replaced by Angular. They changed the name slightly. And they are learning on their own mistakes. And what's better, they are learning from each other. There is a competition. But also, when React came out and Angular wasn't that popular, and React kind of jumped into that niche and had a lot of updates, and then they had the dangerously set inner HTML function, right? So they improved that. They told developers that if you're trying to output unescaped data, you will use this function that has the word dangerous in it. And then Angular, next version, came along, and they renamed the functions that they had before that was called safe HTML. They renamed it into bypass security HTML. So I think they're learning from each other, and they're trying to improve it and also help developers make the right decisions. So there is hope.
There is hope, and there is a little slowly moving up. We learn as we move along.
Yes.
Very good.
Yep.
Other question? Yeah, there is one. Please. There is the microphone coming.
We are coming more from security and audit, so how can we help our developers to improve their security? What should we suggest them to do to improve the usage of such tools and frameworks?
So one thing is, it would be nice to have some sort of rules and procedures for when developers are choosing which framework they're going to use, right? So that they are maintained, they are new, and they have a security page that says, hey, we actually thought about security. And the other part would be to look at, OK, the latest versions of that framework, were there any security updates? Were there any security bugs filed for that framework? And were they actually fixed? So if you could have that step for the developers when they make a decision, when they start using a new, when they start developing a brand new application and decide to use a new language, a new framework, something completely new that the company hasn't looked at before, there should be a step that says, let's assess the security of the tools that we are going to use for many years. So that would be helpful.
Good. Additional questions? Oh yeah, there is one. Always closing this.
Does the use of TypeScript change anything of what you exposed in your presentation?
Yes, use of TypeScript. That's a good question. So TypeScript, because it is the idea is to have the types in the JavaScript. It definitely leads to more secure applications because some of the attacks are now not possible. You cannot, if the application is expecting a number, you cannot feed it a string. So yes, it does remove certain types of attacks. But it doesn't mean that it makes the applications completely secure.
OK. I'm not seeing any additional questions, so we're closing this here. There is a little prize for your PhD. I got you a bit of diploma of chocolate.
Thank you very much.
Thank you very much for coming, Ksenia.
Thank you.